thank you for the invitation to speak here. And I will speak about electrical engineering. I'm working in the ITC, and we are in strict collaboration with Alexandro, celebrado, and Dr. Felix from the mechanical point of view and also for clinical application. So I will speak about the renaissance of patient-specific implants that are normally called custom-made implants. An overview is that it's important to specify that custom-made implants, even if in these last years are more known, but they are quite old. They start to be on the market since the 90s, when I started in the orthopedic field. But of course they were not too much used and very known because it was very expensive and it was very long time the development of one implant. In 2005 there is a disruptive change that marks the difference, and is the metal additive manufacturing that arises on the market and starts a new era in custom-made implants. Then, in the next 5 years, the software companies started to pay much more attention to develop tools for design very complicated geometries that before it was not so important to design because it was not possible to manufacture. So it made no sense. So this is the main difference. There is a summary. The key topics that are communication, design, manufacturing, geometries that you can design and manufacturing, the timing and the costs. In the first stage of the custom-made implants, and then from 2005 to nowadays. Of course, just the communication and the broadband is a big advantage because 20 years ago, just to receive a tomography, it was a problem. 1 week at least, they had to be sent by floppy disk. And also the design tools were thought for manufacturing with subtractive method and not with additive. No? Of course, manufacturing itself, the additive is the main reason why there is a renaissance of custom-made implants. That is because free-form geometries can be done with about no limitation. The limitation is more your imagination than the manufacturing tools. I remember that when I started in the orthopedic fields, it took about 4 or 5 months to make one custom-made implants. And nobody used, at least in Spain, there were very few cases in a year, in all Spain. Now we work with 3-4 weeks, even less. And the costs also, it changed a lot because it was more than 10 times the price of the custom-made implants in the first era was more than 10 times than the cost of one standard implant. Now it's around 2 or 3 times the cost of the standard implants. So we started in 2005 to think about a new way to make implants, starting from the orthopedic needs. We start to produce very high porous geometries with a strong anisotropy and with improved resistance versus metal brittle. I mean, the idea was to use just the space of the missing bone, just to use 10%, 15% at maximum, and then to leave all the rest for the regeneration of the tissue. And with these few materials, the challenger was to be able to be load-bearing the implants. And this is in which we have been working and in collaboration with Alessandro and Alberto. So the main advantages are the elastic modulus just of the material. We've been using always titanium, but before titanium was more elastic than chromo cobalto, but it was very few arguments because it's anyway too stiff compared with bone, with spongy bone or with cortical bone. So what we do we start to do, and the big advantages we saw in the porous structure is that you can build the right building block for your implants. You can fit exactly the mechanical behavior of your implants to the specific needs of the anatomy that have to receive it. So you can avoid stress shielding that is been during a lot of years the main reason for implant failure, and also you can avoid periprosthetics fracture, that is typical fracture when something very stiff is working with something much more elastic together. And then the regeneration of the main volume that can help you to have better results at long time. What we did was to use electrobeam melting. In such a case, I have to say electrobeam melting because we make implants and we have to choose one specific. It's not like a generic one. And we choose ABM because it was the only one that at the moment, in 2010, when we bought, 2009, the machine, was the only one that was already used since 2007 in custom, in standard implants for acetabular cups. And so we decided not have any risk of new process like laser that's been improved afterwards. Our targets were to maximize the respect of a living tissue, so to leave the more tissue as it is as possible, to have the less risk during the surgery, and to avoid any improvisation. And it's normal revision surgery. It's very dangerous because you cannot manage any new situation in an easy way. The idea was, of course, to regenerate volume of bone, not just to replace it. And we had to think about which were the most cost-benefit application where to apply custom-made implants. This is just a flow chart of our working method. That is, we reconstruct with limits or impresarius the tomography. Then we work with stereolithography or with, now I should say not FDF, but it was
no, that's depending on the pattern. When the pattern expires, you cannot use FDF because many companies manufacture
extrusion, no? It's right. Extrusion.
Right.
Then we designed with different kind of software that any implants and any situation needs sometimes different software for some step of design. Normally we don't use only one software for one implant. Then manufacturing, of course, ABM with titanium 6 aluminum for vanadium. We validate the implant and the instruments, the specific one with the model we had been used during the surgical planning with the doctors. And then the main implants have been implanted by handmade, but some of them have been also assisted by navigation. Not here in Spain, but in Argentina we did it. So this is a summary about 150 implants we did in the last 40 months. It's about 30% neurosurgery applications, skulls, main are skulls, reconstruction, 30% maxillofacial reconstruction, 30% orthopedics, and then 10% thoracic. Before to start with implant humans, we made some validation of this concept. It was a quite new one. So to rebuild bone with a structure that is just 10% of the volume, it was, it was fantastic, the idea, but we have to validate that it was possible. And we did it at the beginning in an animal model, in a shaft of the tibia of the sheep. Here we removed 4 centimeters of the shaft of the tibia, and we put a scaffold, a metallic one, and fixed it with the plate and screws. And then after a couple of months, there was already a big callus. That is a first material that fills the gap. It's not as this is plexiform bone. It's not structured bone. And then under the right mechanical stimulus, it starts to a process that is it's about 6-7 months long. There is a process of remodelation, of bone remodelation, that you can after 9 months remove all the synthesis material, and we leave the animals working without any synthesis material during 3 months, and then there was euthanasia and histological cuts. And it's reinforced bone. The idea is that you have already your own bone, but it is still reinforced inside with some 10% of metal that you cannot be able to remove anymore. We just some information about the implant we did in the last years. Different reconstruction of the ankle, especially for the astragal. Sometimes in such a case all the bone, but in some other cases just revision of failed prosthesis. In orthopedic knee, this is a very, sometimes it is the more cutting edge application we are doing. We did 5 cases in the Soli Institute in Italy. It is a research center for and an hospital just for orthopedics. And these are very big defects of young patients where it makes no sense to put a normal prosthesis because they are too young. This was a girl, 17 years old, and now he's still working on 3 years of follow-up, not more. But the idea is to make some patch. This is the patch. It has a base of titanium poroso, porous titanium. Then it is in contact with the bottom, or with the this is the drilling mask to make the defects more precise, and then to put the patch inside. And the surface part, this is cartilage here, and here there is a small line, and the part that is on the left is the implant. It is made by polycaprolactona. That is a biopolymer that can be resorbed and can give a chance to this patient to generate also cartilage. We've been working also in hip, not in stems, because the stems are very high mechanical performances and they breaks. Additive manufacturing is good when at fatigue there is no so much requirements of mechanical behavior. So we have been working a lot, but just in the acetabular reconstruction. We did also a lot of skulls reconstruction. This is not a direct method. We use additive manufacturing for for a model that is that one that helps us to produce the mold of the implant, and the implant is made by celebrado. It's synthetic bone cement. And our application also in thoracic, that we had already seen before. Maxillofacial temporomandibular joint. It's very niche of the market because it's a very small articulation, and then it's not possible to treat with the standard implants. You have to do it by custom solution. Some different jaw defects for tumors, spine in block resection. This is another very cutting edge application. We remove in patients that as metastasis, remove 1, 2, or 3, the maximum level for 4 level of vertebra, and then you have to replace it. In such a patient, you are obliged to have a surgery because the risk that can collapse the bone is too high, and then the patient can have severe injuries in the spinal cord. Different segmental reconstruction in upper and lower limb, and some other application in elbow and somewhere. Any implant is different from another one. So about the results, we can say that cranial maxillofacial surgery was the first field to give to show interest in custom-made implants, probably for the aesthetic implication, because everything is much more exposed, and then you need a precise reconstruction. The orthopedic field had been more prudent, but in constant increasing, and it's an application that require much more experience, higher mechanical performances, and there is a big amount of different things, and you need to be trained a lot. Thoracic surgery is another very interesting emerging field, because the main topics of thoracic surgery is not the bone. The bone is just a part in each of the thoracic. No? The thoracic surgery is more of soft tissue than the bone. No? And it's something that is a field that started more recent, but it's sometimes the field where it's more difficult to design an implant, because the implant has to be very elastic to follow the movement during the breath. So about the developing time, we are about 2 weeks of mean time, but sometimes you have to hurry up when there are tumors that are very urgent, and we have to do in 3-4 days. No? We don't like it all, but sometimes you have to do it. Then about which are the applications that are compatible are implant replacement, primary implants in singular cases, normal, or patient very young, or with anatomy very big deformities, except temporomandibular joint that for his size is especially interesting for custom-made implants. Of course, any kind of congenital degenerative malformation, tumors, all of them that need reconstruction, big reconstruction of bone, and also non-unions that are fracture that doesn't fit and they didn't fix it, that you have to remove part and then you have to repeat. Of course, traumatism for timing is not compatible with the custom-made implant, because you have to treat traumatism in the first 24 of 48 hours. So you have no time. About the human factor, the surgeon engineer communication, it's the critical point that set the development of the implant, because we have both to agree about the design. And so most of the time we lose together to have the right design. But when you start to work with the same team, with the same surgeon and the same engineer on new implants, then the time is shorter and shorter. And we can say that about all the surgeons that start to use patient-specific implants, they normally repeat, and their colleagues will start to. About the organization, we can say that it is quite difficult to achieve a critical mass, to have, from the economical point of view, and let's say a sustainability of the service, but also to have the minimum number of cases to reach the experience you need for do this job. And this is a critical point for the development, for more common application, because there are still few cases and are all around the world. I mean, you have to be in a big geographic area to reach few implants. And this is a problem that can be solved working in another model with the hospitals. I mean, I'm convinced that inside the hospital has to be implanted some engineering tools to do more custom-made implants in the future. So our conclusion are the technology at the moment is already cost-effective. It's something that is doing and is appreciated. The change of paradigm has been already done. I mean, the idea that are long timing developing and expensive, it's the past. We can still improve a bit the surgeon-engineer communication. The patient benefits are immediate because the surgical time is shorter and the risk is less, and also we preserve much more tissue. But the benefit from the health economy point of view, it is at medium term. I mean, it's because if you do something in the best way, then sometimes you can skip or avoid one revision, but you have to wait some years before to see this advantage. It is possible, sure, to regenerate, not just to substitute bone, and probably it is necessary also to develop a new generation of patient-specific implants that is supported from some standard elements that can be combined with a custom solution. Thank you very much.